After discussing the mechanism by which we locate earthquakes, I thought we'd take a little break and talk about the effects and devastating destructive effects that earthquakes have on towns and populations. So many factors influence how destructive an earthquake, including each of the following. So obviously the distance to the epicenter is going to play a huge role, okay? If you're closer, then those earthquake waves aren't going to have as much time to dissipate and they're going to affect more, especially those surface waves like the Love and the Rayleigh ones. Also, the geology of the region has an impact. Some rocks are just sturdier in nature, okay, like granite. And if you have rocks that aren't as sturdy, then an earthquake is going to rupture those. That affects it. And also the magnitude, which is something we'll get into in just a little bit. So here's some examples of some effects earthquakes can have. Ground shaking is number one, it's kind of obvious. And right here I have three statements, and we're going to play a fun little game called true or false to each of these statements. Statement one, great earthquakes are powerful enough to swallow buildings whole. And this term great earthquakes just means any earthquake with a magnitude, again, we'll discuss that later, with a magnitude greater than 8.0. So great earthquakes are powerful enough to swallow buildings whole. True or false? That is a big fat false. You only see earthquakes opening up and swallowing people whole in movies. I have no idea why people think that. Okay, it doesn't even make sense because earthquakes, the entire mechanism is based off of friction. So those plates need to slide against each other. Okay, it makes no sense for the plates to move apart. That's a divergent plate boundary. And while earthquakes happen around divergent plate boundaries, the reason this happens is this plate that's moving in this direction is going to slide next to a plate moving in some other direction. All right, the second statement right here. Some earthquakes are famous for having sediments turn to liquid. This statement's actually true. The process is called liquefaction. Whenever an earthquake is so intense that the structural integrity of the soil or sediments around it just completely goes away and the solid kind of turns to a liquid. A famous earthquake responsible for this is one in Japan in 1964. Essentially, the soil turned to liquid, so all the buildings fell on their sides. This third statement says California will one day be pushed into the Pacific Ocean. When I read that some people actually believe this, I got really opinionated for no reason. That is absolutely fiction and false. Science fiction, okay? I don't know how people get these misconceptions, but rocks are not powerful enough to throw an entire state into the Pacific Ocean. They don't have enough energy built in them. So that is definitely false. Okay, fire is another consequence. There's a famous earthquake I'd like you to know, and that's one that happened in 1906 in the city San Francisco. So 90% of the damage in the famous 1906 San Francisco earthquake was caused by fires. Okay, and there are several reasons for this. Earthquakes moving around back in ye olden days without electricity, it knocked over fires and fireplaces, and all the fire got out of control. Plus, they probably didn't have an established fire department back then. But today, cut gas lines and damaged electrical grids are the ones that start most of the fires. Also, if they cut off the water supply, that's very deadly because firemen and firewomen can't really get to it in time. Speaking of water, let's talk briefly about tsunamis. Okay, earthquakes that are underwater generate a massive collection of water that can travel for miles until it reaches shore. So, tsunamis are kind of devastating because they strike coastal regions like Hawaii or Japan, California, especially those coasts. And basically, people have made detection systems, especially in the Pacific Ocean, that monitor earthquakes, and they also monitor whether or not it's a tsunami. Whenever those waves go across the ocean, people don't notice them because they're moving so fast, but the amplitude or the height of the wave isn't big enough when it's traveling. But all that water keeps collecting and collecting like a snowball. And eventually, whenever it gets to the coastal areas, you get some recession of water that happens. And I wish I had a picture right here, but all this water just gets built up, and you have some areas of bare land where there should be oceans. So the question, how would you know if a tsunami is about to strike? Well, probably one of the biggest tells is if a substantial amount of coast withdraws from the area. Okay, and what happens is fishermen and other people go to those places where fish are just lying and there are actual coral reefs there for no reason, and they start picking it up and wondering what's wrong until the tsunami actually strikes them and kills them. Okay, landslides are the third consequence, and hopefully this is somewhat explanatory. Yeah, like mountains and avalanches have been known to destroy towns. Okay, how do we measure the strength of an earthquake? Well, there are two methods. Earthquakes can be measured based on two things, intensity and magnitude. Intensity first. Intensity is an arbitrary assessment of how strong an earthquake feels. Okay, so it's highly subjective, and we use the modified Mercalli intensity scale, which rates the intensity of earthquakes on a scale from 1 to 12 in Roman numerals. So that would be I to XII. And I encourage you to go and read this. No, you're not going to have it memorized. I'm probably going to put it on your reference sheet, but I just kind of think some of this is funny. Also, some of the synonyms they use for destructive, I would have used cataclysmic. I really like that word. But yeah, 1 is obviously like instrumental, only detected by instruments, and 12 is catastrophic, total destruction. So I just kind of find it funny, but it is useful in surveying damages. Like insurance companies use the Mercalli intensity scale all the time. I actually read a PDF from some insurance company in Missouri, and all it talked about for assessing earthquake damage, all it talked about was the Mercalli intensity scale. So that is great for assessing damages. Magnitude is a quantitative measure that is based on the amplitude of the highest recorded seismic wave. Okay, so let's talk about what an amplitude of a wave is. So you have a seismogram that does something like this, and hopefully your lab kind of cleared that up. Okay, so you have some primary waves, secondary waves, surface waves. If you draw a line straight through the middle, basically the vertical displacement, either up or down to the pinnacle of these waves, is going to get you your amplitude. So this is an amplitude, that's an amplitude. You can go up or down. So if we're talking about the biggest wave, it would either be this one or this one would give you the highest amplitude. So the magnitude is actually based off of these amplitudes. Magnitude values are on a base 10 logarithmic scale. I'm assuming that in your algebra or pre-algebra classes, you've never really been exposed to logarithms. So I'm going to give you a very brief introduction to logarithms, even though I'm a math guy and I'm very biased. So logarithms kind of work like this. They work like this. Here's the game. How many times do I have to multiply 10 to get 10? Well, hopefully 1. 10 just one time is 10. Okay, how many times do I multiply 10 to get 100? Well, 2, right? You multiply 10 times 10 to get 100. Okay, how many times do you multiply 10 to get 1,000? Hopefully by this point you might have noticed that you just count the number of zeros present. So 1,000 has 3 zeros, so you need 3 tens multiplied together to get 1,000. Okay, but what if I asked a different question? What if I asked, how many tens do I have to multiply to get 40? Well, I don't know. You can type this into your calculator. Basically just hit log, and it's assumed that you're dealing with the number 10, and just type in 40. But I know that it's going to be greater than 1, but it's also going to be less than 2, because 10 would get you a result of 1, and 100 would get you a result of 2. So it's somewhere between 1 and 2. I would guess like 1.4. You know what? You might actually be able to do this with your calculator. So 40 and log. Here's the log button. So it's 1.6. My bad. Yeah, it's 1.6. So this is basically the structure behind what a logarithmic scale is, and this is what they base magnitude on, and that is the Richter scale over here. Okay, so these numbers are what you see in the news. Like, oh, this earthquake had a magnitude of 6.8. Well, that 6.8 came from this logarithmic system. Each increase of 1 is a 10-fold increase in the amplitude. Just look at what happens when we go from 1 to 2. If I increase from 1 to 2, we're just adding another 0. We're multiplying by 10. This is 1 10. This is 2 tens. So it's just a 10-fold increase. A 10-fold increase from 2 to 3, 3 to 4. But I want you to note that that increase only accounts for the increase in the amplitude of the highest wave. Okay, just because we increase 1, we're not talking about the energy. In fact, in each increase of 1 is about a 30-fold increase in the energy that's released. Amplitude and energy are related, but they are not causal relationships, right? Amplitude does not cause high energy necessarily. There are other factors that contribute to it. That is why this question bothers me. Right? I got this off a Science Olympiad website. It's a C division level competition from earthquakes. And it says a magnitude 4 earthquake. Okay, so all these choices have 2. And we want to compare magnitude 2 earthquake to a magnitude 4. Well, if we go up right here, we're essentially saying if I go from 2 to 4, what's happening? Well, there is a 10-fold increase from 2 to 3, and there's a 10-fold increase from 3 to 4. So there's a 10 times 10 increase in the amplitude. If you look down at all the choices, though, the correct answer is D, but I don't want you to circle that because if you read the entire statement, it says releases 100 times as much energy. That is wrong because technically each increase of 1, like I said before, is about 30. I think exactly it's like 31.5. So what you're really saying is since each numerical increase gives you this much increase in energy, it's 31.5 times 31.5 as you go from 2 to 3 and 3 to 4. And I don't really know what that is off the top of my head, but I'm guessing it's really, really close to 100. Times 31.5. 30 times 30 is 900, but this is almost 1,000, which means the correct answer should be E. This question is wrong. Okay, so I don't know if I talked about this before, but that is called the Richter scale if you use magnitude. It's the Mercalli scale if you use intensity. So let's talk about some pros and cons of both scales. So the Richter scale is numerical. Not to say the Mercalli scale doesn't have numbers, but it's easy to graph over time. It's the more conventionally used one in the news. Okay, so if they talk about it in the news, they're normally going to talk about the Richter scale like, oh, this earthquake had a magnitude of 8.6. Okay, the cons, unfortunately, the highest amplitude of all the seismic waves might not be representative of the whole earthquake. Okay, like I said, if you had a seismogram, that looks something like this. Okay, that amplitude is what your magnitude gets based off of. Is that really fair? Not really, because the majority of the earthquake was, pretty non-reactive. Okay, let's talk Mercalli scale. Remember, that's the one based on intensity. Seismologists can construct things called intensity maps. When they're surveying an area that's just been hit by an earthquake, they can look at specific areas that might have been burned by buildings, or the buildings might have fallen over, people might be screaming, and they basically classify those and give those areas numbers that correspond on the Mercalli scale. And they give a rough estimate of an earthquake's strength. Actually, no, they give a rough estimate of an earthquake's location. Because if you see a lot of buildings in one area that have all fallen over, you know the earthquake's probably close. So it's a rudimentary estimation of earthquake location. It's also really good for surveying damage. Like I said before, insurance companies love this scale. Unfortunately, it's subjective. You're not really able to scientifically analyze it, which does us no good. So we're going to probably refer to the Richter scale, but there's actually another scale that takes more into account. Okay, it's called the moment magnitude scale. Sometimes you'll see it seismic moment magnitude. It's just another scale, and all I need you to know is it's more holistic, and that's a fancy way of saying it takes more into account. It takes fault lines, it takes the sturdiness of the rock, the shear stress, it just takes more into account. Okay, normally I've seen it give higher numbers than the Richter scale, like 9.5, 9.6 instead of like 8.5. So people have been turning to this more recently in the news, but I would still stick with the Richter just to be safe. But know that this is a thing. Okay, here's an excellent graphic of the Richter scale and what each of these represent. Note it is logarithmic, but each increase in one gives a 10-fold increase in amplitude. Finally, just in case you ever wanted to know this for life, if you know the difference between the S and P waves and you also know the amplitude, you can graph them on this little organizer right here and draw a straight line to get the magnitude. So I just thought that was pretty cool. Right? In my next video, I'm going to discuss the very pressing question, can we predict earthquakes? And I encourage you, before watching that video, to ponder upon that question yourself. Can we predict earthquakes? And I'll see you in the next video.